think I just broke my X broadcast, but I don't really care. It's fine. All right. Looks like at least Twitch is working. All right, cool. Cool. So, where do we leave off? Oh, we're going to read this article here. And it's 7 o'clock. I don't think I'm getting to bed at 8 tonight. Usually I try to get to bed by 8, but I don't think that's going to happen. So, maybe I'll just work through that until I get really tired. And then I'll just like, I already ate dinner. I already did my cardio. So, yeah, I'll probably just work through until maybe about 8:30. Something like that. And then crash. All right, a simple ISPC example. So ISPC, Intel, ISPC stands for Intel, is the Intel, I have no idea. Implicit SPMD, single program multiple data, implicit SPMD program compiler. So the key part there is the SPMD program. C you get for free because obviously it's a compiler. Implicit SPMD compiler, program compiler. Okay. Are any compilers not program compilers? It's single program, multiple data program compiler. It's kind of crazy. So it's an Intel implicit single program, multiple data program compiler. Okay. Here's a walkthrough of a simple example using ISPC to compute an image of the Mandelbrot set. The full source code for this example is in example CPU Mandelbrot directory of the ISPC distribution. Below is a lightly modified version of that example. For example, we have alighted some of the details related to benchmarking and writing the final output image. They're actually that are in the actual Mandelbrot CPP file there. First, we have some code in the main program file, Mandelbrot CPP, which is implemented in C++. We mostly have a regular C++ source file that sets a number of variables and that drive the overall computation, allocates memory to store the results of the Mandelbrot set computation. The call to Mandelbrot ISPC is a subroutine call, although in this case, it's calling out to code that's written in ISPC rather than in C++, because ISPC compiler generates regular object files using standard C++ calling conventions. This kind of close interoperation between the two languages is straightforward. So you just call it like a regular function. Cool. Here's the start of the definition of the Mandelbrot ISPC function. This is their main. We have width and height as units. And then we have our coordinates for the viewports that we're going to be generating. And so this is from the original implementation. So I think all of their stuff, they just pulled the code from Intel here. Max iterations is 256 iterations. And then we create our buffer, which we're going to store our results in, and that's just going to be width times height. So this interface, this set of arguments makes a lot more sense to me than the num rows and height that they were using in the other, the first assignment. That set of arguments was like, it's kind of nasty, because height was separated but width wasn't, and they were floats, I think. Yeah, I forget why, but it was very much confusing, I should say. The set of arguments for that function. Anyways, so here's the start of the definition of the Mandelbrot ISPC function that ISPC compiles. This function is defined in Mandelbrot ISPC. So do you have to have header files for ISPC files? I imagine so. There are four main things to notice here. The export qualifier, so this is what we're talking about here, indicates that this function should be made available to be called by C code, not just from other ISPC functions. This function directly takes parameters passed by the C code as regular function parameters. No API calls or runtime library are necessary to set parameter values to pass to this function. Parameters are all tagged with the uniform qualifier. This qualifier indicates that the variable has the same value for all of the concurrently executing program instances. It is discussed in more detail in the ISPC user manual. Any values passed from the application to the ISPC program must be uniform. The pointer to the output buffer is passed as a unsized array. Just like in C, arrays and function calls are converted to pointers, the first element of the array. Parameter could also be declared to just be a pointer. Like the other function parameters, this buffer is passed from the application to the ISPC code without any copying or reformatting as would be required with a driver model based implementation. Function implementation starts by computing the step between pixels in the X and Y directions. Step between pixels. Okay, so this is like, that's why it's called dx and dy, because it's like the discrete unit. Is that what D stands for in calculus? I'm curious. Let's ask AI. In calculus, what does D stand for in dx, dy? I know what it means, but I want to know what it stands for. It represents a differential operator in the Leibniz notation. Yeah, I know what it means. Yeah, differentia of x. Yeah, it's like a delta, an infinitesimally small delta. I was hoping it'd be called discrete because that would make a lot of sense in this context. A discrete unit of x and a discrete unit of y. Next, the function loops over pixels of the image with a doubly nested loop. The outer loop is a regular loop over scan lines, while the inner loop introduces a new looping construct provided by ISPC for each. In general, for each specified, I like the way that they give you a brief introduction to the code and you can kind of glance down at the code below. In general, for each specifies parallel iteration over n-dimensional range of integer values. In this case, it specifies parallel iteration over a 1D range of pixels in a scan line. Each time through the loop, the iteration variable I takes on values corresponding to a small range of the domain. Let's reread that. In this case, it specifies parallel iteration over a 1D range of pixels in the scan line. Each time through the loop, the iteration variable I takes on values corresponding to a small range of the domain. Okay. So each line we're processing in parallel. So it's probably going to use SIMD for that. Because I remember learning, I think it was just from the lecture material, that ISPC also does auto threading and stuff, where it'll create threads for you. Okay. If ISPC was generate code to run an 8 wide parallel fashion for an 8 wide AVX SIMD unit, I would have the values 1, 2, 3, 4, 5, 6, 7 across the group of executing program instances the first time the loop executed, 8 through 15 the second time the loop executed, and so forth. See the other examples in the ISPC distribution for other examples of using for each to perform this mapping for other computations. Inside these loops, we first find the floating point x and y values that correspond to pixels at which to compute the Mandelbrot iteration counts. Note that these are also straightforward calculations. Recall how the I variable is initialized by the for each loop to see how values derived from I have different values across the program instances. In this case, corresponding to the number of x positions at which to perform the Mandelbrot set. So J is going to be the row, and I is going to be basically the pixel in the row. It has to be the pixel, right? So we say I times dx, and we start at x0, and we add that. So x0 is going to be the upper left, probably, if we're going scan lining downwards. I think when I did it last time, the code, it was in the bottom left. Bottom left would make more sense because x would increase going, yeah. Bottom left, it's in the bottom left, yeah. Once it's figured out the coordinates at which to compute the number of iterations, the program finds the appropriate index into the output array for them and calls a subroutine to do the actual computation. Okay. Here's the implementation of the Mandel routine. It takes real and imaginary coordinates and a maximum iteration count and applies the iterative computation that defines the Mandelbrot set. Although this appears to be a serial function, only computing one result for one pair of input coordinates, recall that ISPC's execution model is as single program multiple data. The program compiles down to run in parallel across the elements of the SIMD unit. For example, computing 4 results from 4 input coordinates in parallel on a 4 wide SSE unit. Wonder how they accomplish that. I don't really want to look at the disassembly to find out. To compile this example, install the ISPC compiler in a directory that is in your path. And run make on macOS or Linux. Or use the CMake on Windows. Note that ISPC compiler generates regular object files that you can just link with object files compiled with C++ compilers. Here's the assembly language output from compiling Mandelbrot ISPC source code with emit ASM command line option. Okay, I'll read the disassembly or the assembly here. So I was more curious about just like because I can't read this stuff really. I want to see what the Mandelbrot looks like the actual Mandelbrot function. Wait a minute. Oh, there's no symbol for it because it's not exported. But this thing, Mandel, ideally it'd be in here. Oh, might be. Mandel FFI exits. Okay, I'm not gonna read that. They're gonna make ISPC 02 target AVX Mandelbrot ISPC object output -H for the headers. It creates a header so you can link against it. Or sorry, it creates a header so you get 4 direct declarations for the exported functions that you can include. Okay. After the executable is built, running it benchmarks a serial implementation of computing the Mandelbrot set and the ISPC version. You may want to compare the files Mandelbrot ISPC and Mandelbrot serial CPP to see a few syntactic differences between the C++ implementation of this computation and the ISPC implementation. On a second generation Intel Core i7 CPU, doing this computation in parallel across the SIMD lanes of a single core gives a substantial speed up. That is like 6, almost 7x. Probably around 6. Yeah. 6x. Here's a downscale version of the image that the program generates. Note that all of the exposition up until now has been related to harvesting the available parallelism from the SIMD unit in a single CPU core. To fully use the system's computational resources also requires parallelism across the CPU's cores. Modern CPUs may have from 8 to dozens of processing cores, each of which has a SIMD vector unit. Okay. Thanks to the fact that ISPC cleanly interoperates with application C code through a regular function call, one option would be to rewrite the application code to be multi-threaded, for example, using the task scheduler provided by the Intel thread building blocks or Microsoft's concurrency runtime, and to then have parallel tasks that were in turn partially or fully implemented in ISPC. The second option for parallelizing code across cores is to use the built-in functionality for launching concurrent tasks that ISPC offers. ISPC language provides constructs for launching asynchronous tasks that can execute concurrently with the rest of the program. See the directory examples CPU Mandelbrot task and the ISPC distribution to see how to parallelize across both cores and the SIMD units. I assume they're using P threads, right? Do they do their own threading implementation? Can I go to the GitHub? Where's GitHub issues hosted on GitHub? Okay. Well, let's just ask AI. ISPC tasks, are they full POSIX threads when compiling on Linux? Do they use OS libc code, or are they their own implementation of threads? Function pointer plus arguments, metadata for scheduling, chunk of work that can be stolen, executed. Execution is backed by a runtime thread pool. Okay, so you provide some type of thread pool via this lib ISPC. ISPC runtime, task system runtime uses POSIX threads. Okay, that's what they should do. Or equivalent OS threading APIs on other platforms. Creates a fixed or semi-fixed pool of worker threads at startup. Yeah, so that's one of the downsides is like they control the threads, and all you're doing is like calling into code that like uses the thread pool. pthread create, pthread mutex, pthread con, atomic operations, sometimes OS synchronization primitives, but does not implement its own threading primitives from scratch, builds on OS libc facilities. We schedule jobs executed by pthread back worker thread pool, not how popular is ISPC? So SIMD, and you would say that SIMD intrinsics and pthreads are more popular solutions to parallelizing code. Goes to OpenMP SIMD pragmas until TBB in usage domain CUDA, but CPU side and narrower than to general purpose languages. Even though it's good, it didn't become mainstream because SIMD is increasingly auto-vectorized. Modern compilers, LLVM, GCC, Clang are much better than they used to be. Rust, C++ intrinsics already dominate low-level work. Most performance teams prefer AVX intrinsics or compiler auto-vectorization and pragmas. Ecosystem lock-in is weak. ISPC is not standardized, not part of major language ecosystems, mainly Intel-driven, even though open source. SPMD model is nice but specialized. It's great for run this kernel over many data lines, but less useful for general program structure. Where ISPC still wins. It's still chosen when you want SIMD performance without handwriting intrinsics. I actually kind of like the intrinsics and like having to think about intrinsics, portable AVX, SSE neon code, explicit control over vector lanes, CPU side GPU like kernel style programming. In those cases, it can be generally excellent. Bottom line, ISPC is a well-designed but niche SIMD programming compiler used mainly for high-performance graphics. That's the reason why he's using it, because he's a graphics guy. Simulation and CPU kernel workloads, not a mainstream general-purpose technology. If you want, I can also compare it directly to AVX intrinsics, OpenMP SIMD, C++ standard SIMD. Oh. And then SIMD intrinsics, pthreads are significantly more widely used in real-world systems programming than ISPC. They solve different layer parallels of problems, do they? It's not a perfect substitute comparison. SIMD intrinsics, are there popular downsides? Eigenblast, FFTW, etc. EIGen library. Kind of want to check these out. Blast. So that's linear algebra is something. Library. I think it's C++ linear, basic linear algebra subprogram. And then FFTW library. I'll check those out later. Okay. Game engines, image video codecs, databases, vectorized execution engines, compilers themselves, why they're popular: direct hardware control, maximum performance potential, stable, standardized across compilers and architectures, no specialized toolchain needed beyond compiler support. Downside, hard to write and maintain, not portable across SIMD widths. That's the thing, is like, I like writing the intrinsics, but I wouldn't want to have to do it for every freaking version of AVX. I guess it's not too bad of a hassle, but it'd be nice if there was some type of like, I program in this model and then you just provide the vector width. And then I don't make any assumptions about the vector width other than it's like a power of 2 or something. So yeah, SIMD intrinsics are a mainstream low-level optimization tool. POSIX threads, pthreads is foundation of CPU parallelism on Unix-like systems, web servers, databases, runtimes, game engines. Basically everything is multi-threaded. ISPC is more like a specialized abstraction layer over SIMD and threading. Data parallel inside core, SIMD intrinsics. Task parallel across cores, pthreads, OpenMP, TBB. I do want to check out these two. OpenMP and TBB library. ISPC tries to generate SIMD code like intrinsics, distribute work across threads like pthreads, OpenMP, hide both from the programmer, but it's not as universally adopted as either layer. Key takeaways: convenient abstraction for providing both, but used in niche high performance domains. Personally, I'd rather just do the intrinsics and pthreading myself instead of like writing in this weird language that Intel concocted. And like, I understand like a lot of great engineering went into this from what I understand about learning about this last year, but it's like, okay, it's Intel vendor specific. It's a non-standard language. It's like its own little language. What else? Oh, it doesn't allow you to manage the thread pool from what I understand. So its concurrency model is, it's imposing its own concurrency model on you. What else? It's kind of giving you a level of abstraction over these primitives, which is gonna box you into their model of using these things. I could see maybe it being super useful if, and the other thing is it might be intellectual property issues, but I don't think there is. It says it's open source. Um, but I could see it being really useful in situations where, like, a part of your build process, you just want to like have this thing do all the SIMD auto vectorization of the entire code for you. It's like, okay, well, it's really good at that, and if GCC and Clang are not auto vectorizing enough for you, you can just throw your thing in this, have it auto vectorize, and then call into it because it's just a regular like C calling convention. So I could see it being useful for like areas where you want to like implement these things. But my gut instinct is intrinsics is a more powerful and generally better solution because it's standard C, C++. It's built into all the compilers, open source, broadly adopted, broadly understood. It gives you full control over the actual instructions that you're emitting from the compiler. Its downsides, though, is it's not very portable. You know, you're hard coding vector widths. So you have to do a little bit of like, you know, I'm creating this kernel. It's specialized. I guess templating could help you here, but basically you have to create your algorithms and then specialize them for all the different vector widths. And then at runtime, when the program is executing, you need to go through some type of function that chooses the right vector width implementation, which isn't too hard to do, I don't think. And the other big thing with using your using pthreads yourself, if you want threads, is that you get to choose your own concurrency model. So a lot more control with pthreads and intrinsics. That's the takeaway from that. All right. I'm not going to dive into this stuff anymore outside of what the problem asks for. So I went through the walkthrough here. Is that the walkthrough? Yeah, here. Okay, we went through the walkthrough. Compile, run the program. Let's go back here. Jump to prog 3, I guess. I'm in the wrong directory. Jump prog 3. Get at all, get DC. Okay, we're on problem 3. Make. Get status. Might do get ignore here. Yeah. Add these to the get ignore. Okay, dokie. So we made up our stuff. Let's cat out our makefile. Oh, I remember looking at this a couple days ago. So it's using the pthreads. Okay, we got a bunch of stuff going on here. But the main thing is it generates this Mandelbrot ISPC. That generates some ppm files, which you also want to git ignore. Star.ppm. Okay, and then I'm going to say display Mandelbrot serial. So that's our serial. Oh, wow. There we go. Okay. It's getting resized here as I change it. So it's a full Mandelbrot set. Is this thing at do a view 2? Let's do Mandelbrot ISPC now. Same thing. Alright, I'm gonna close that if I can. There we go. Okay. I'm gonna pull this out here. I think I should zoom in here a little bit too. Alright, you're coming with me over to here. You're actually gonna go in as a tab here. Can I not do that? Because this is incognito. Is it? No. Go up here as a tab, bro. There you go. Actually, probably better that way. Okay, what does it want us to do? What you need to do. Compile, run the program. Did it. ISP compile is currently configured to emit 8 wide AVX2 vector instructions. What is maximum speed up you expect? So this will be in a write up, I guess. Vim write up. What is the maximum speed up? So it wants us to answer those questions. Describe the parts of the image that present a challenge for SIMD execution. That's a statement, not a question. Shouldn't have a question mark there. Comparing the performance of rendering the So we're just hypothesizing here? I don't understand. What is the maximum speed up you expect given what you know about these CPUs? Well, based on the description of the algorithm that I read last session, so it's row by row, which is going row by row throughout the entire thing. If you did pixel by pixel, like column by column, that would be an O of n, obviously. And well, I guess the runtime is going to be based on the maximum. If a pixel is easy to compute, it's going to be computed quickly. If it's hard to compute, it's going to take a while. And we're doing it all serially. So compare with serial. The parallel execution with, what did it say, 8 wide? Parallel can expect 8x speed up, but limited by hot pixels, slowing down the execution of entire vector of pixels. These are just like general points I want to make. It's not actual prose. Okay. Given we are using 8 wide SIMD vectors to compute the set, a naive estimate of a speed up would be 8x. However, each pixel in a vector is, can take a variable amount of time to compute, and all pixels in the vector, in a vector, need to wait for the slowest pixel to finish before the, what'd you say, finish, that's assumed. Given we are using 8 wide SIMD vectors to compute the set, a naive estimation of a speedup would be 8x compared with a completely serial, single threaded approach. Are they using threads in here? I don't even know. SIMD, or sorry, ISPC, Mandelbrot, ISPC. So the Mandel is obviously like this needs to be masked out. And then ISPC, Mandelbrot. Is there task? Yeah, there is a task here. So this is the task one. Did he talk about tasks yet? Let's go back up here. I don't think he has. Maybe part 2. Yeah, ISPT task. I guess we don't have to consider tasks. So what we'll do is say here will be part 1. I think he said part 1 up here, right? Yeah, part 1. Given we are using 8 wide SIMD vectors to compute the set, a naive estimate of a speedup would be 8x compared with a completely serial single-threaded approach. However, each pixel in a vector can take a variable amount of time to compute, and all pixels in a vector need to wait for the slowest pixel to finish. This will reduce the performance gain from parallel execution. Yeah. So what is the maximum speedup you expect to? What might the number you observe be? Consider the characteristics of the computation you're performing. I think I've already covered that. Describe the parts of the image that present a challenge. For for SIMD execution. Compare the performance of rendering different views of the Mandelbrot set. I don't need to do any of that. I think this statement pretty much summarizes the entire gist of it. We remind you that for the code description in this subsection, the ISPC compiler maps gangs of program instances to SIMD instructions executed on a single core. This parallelization scheme differs from that of program 1, where speedup was achieved by running threads, multiple cores. If you look into detailed technical material about CPUs in the myth machines, you will find there are a complicated set of rules for how many scalar and vector instructions can run per clock. For the purposes of this assignment, you can assume that there are about as many 8-wide vector execution units as there are scalar execution units for floating point math. Alright. So I guess the first part is just like getting familiar with ISPC code. It's not actually fixing anything. Okay, part 2. Tasks. SPMD execution model and mechanisms for each facilitate the creation of programs that utilize SIMD processing. The language also provides an additional mechanism utilizing multiple cores in ISPC computation. This mechanism is launching ISPC tasks. See the launch to command in the function Mandelbrot ISPC with task. With tasks. Mandelbrot so rows per task is height divided by 2. So each task is going to work on a half of the image. And then we do a launch 2 to create 2 tasks. I guess this is another ISPC custom language thing. The custom language is a little too much. Like for general purpose, I understand this is like specific problem domain is parallel computing, but a general purpose language like C++ is more than capable of doing what you need here. They just wanted to like do really fancy compiler and language stuff, which I don't blame them. It's fun, I'm sure. But it's asking a lot for programmers to like deal with a totally different, or not even a totally different. It's almost worse when it's something that looks like C, smells like C, but isn't C. And it's like, what else isn't like C? I'd rather just have an entirely different language so I don't have any assumptions that need to be falsified. But yeah, I guess, I don't know. I feel like it's a big ask to have programmers use a special language. I would rather them I'd rather them have some type of preprocessor step that then compiles into C intrinsics, C++ intrinsics. I feel like that would be like a pretty cool way of doing it instead of implementing a compiler yourself. It's like, we just take this special syntax and we convert it into the C++ that the compiler can handle, the general compiler. Okay. See the launch to command in the function Mandelbrot ISPC with tasks. I mean, it's virtually identical type invocation. This command launches 2 tasks. Each task defines a computation that will be executed by a gang of ISPC program instances. As given by the function Mandelbrot ISPC task, each task computes a region of the final image, similar to how the for each construct defines loop iterations that can be carried out in any order. And in parallel by ISPC program instances, The task created by this launch operation can be processed in any order and in parallel on different CPU cores. What you need to do, run Mandelbrot ISPC with the parameter -- tasks. Okay, let's do that. What speed up do you observe on view 1? What is the speed up over the version of Mandelbrot ISPC that does not partition that computation into tasks? It's a serial. We do Python 442x. Okay, so we got an 8x speed up. If we do view 2, 3x, view 3, yeah. Okay. Let's do display. I don't have to do that. Part 2. What speed up do you observe on view 1? Okay, so we need to run this with the tasks, view 1 and view 2. Let's copy this here. Go down here, paste it. Guess he wants us to do these separately. Just put them out there. View 1 has a speed up of 8.1x. Sorry, 8.1x. 1.8, I guess. Which is about 2x the speed up of the regular ISPC without tasks. So if we go back over to ISPC, this guy, so he's calling launch to Mandelbrot task ISPC task. This thing then does a for each, very similar to the other one, except it does a slightly different computation here. And it marks these things as uniform. Okay. There's a simple way to improve the performance of Mandelbrot ISPC tasks by changing the number of tasks the code creates by only changing code in the function Mandelbrot ISPC with tasks. You should be able to achieve a performance that exceeds the sequential version of the code by over 32 times. How did you determine how many tasks to create? Why does the number you choose work best? Okay, so we got to do this guy here. ISPC. I'll just do 32. 32. Make clean and make and Mandelbrot ISPC tasks. Oh, we got a core dump. Nice. I'm not going to debug a core dump. Oh, we need to do it. 32 here. Okay. So we got a 48x speed up. Let's keep on pushing it. Let's do 64. Divided by 64. 50. So that's a 45. What's 32 and 16 would be 48. 16. Oops. So I think 32 is the sweet spot. Got 39 on that one. 36. 38. If I go up to 48 here. Start getting bugs. $45X. My guess is that 32 is optimal because I have 32 threads on my machine, hyperthreads. I wonder what 16 would do here. 16, 28, okay. Okay, I'm gonna do something here where vim makefile. The thing that compiles here, the ISPC O file here, can I say ISPC flags? Oh, it's already there. Okay, so we're gonna say CP prog to generate something. Generate data here. Then generate data. So in here, we're gonna do a different widths. I need to quote this stuff to keep it from freaking out. What is the ISPC flag for AVX 512? I'm currently using, we just want to have larger vector sizes. I3216. What does this SKX mean? Okay, let's do, actually no, let's do that. 03 arch disable FMA pick dash D task count equals $N, and then this is going to be the task count and the speed up, and we're gonna do from like, let's do like 8, 16, 32, 64, maybe 4. Yeah, 2, 4, 8, 16, 32. We just do the powers of 2 there. Make clean. This is where we run make with this stuff. Okay. Boom, boom, boom. Oops. If I go back here, D vector width. Oops. D task count. Okay. This is going to be a different program. This is going to be Mandelbrot ISPC and task, and then I want to grep for from task ISPC, speed up from task ISPC, and then we're just going to set out search for parentheses. Actually, no, I'm just going to TR it. TR parentheses space, and then we could just X. Can I do both of them? Yeah, there we go. Awk out print $1. There we go. Whoa, that's pretty consistent. There we go. Let's grab this whole thing. Okay. Let's do it. And we run the generate data. Shouldn't take too long to run it. All right. And then we're going to say cat out data. Oh, wow. Task count macro redefined. Oh, I have to do the ifdef around that. Okay. Mandelbrot, ISPC, no, dot, ISPC, yeah, this one. So up here, I need to say if not def task count and if something like that, make clean, make clean, make. Okay. Generate data. Okay. Cat out data. 64. Seems off by 1. Not to mention we didn't get the last data point. So let's see what's wrong with this. Well, just do like that. Error, ISPC output differs from sequential output. So 64 basically we can't do because it differs. Wonder why that is. Maybe there's not a join going on or something. That's weird. It is weird. I'll ignore that for now. Let's go back to generate data. We'll put this guy back and we'll delete 64 out of the queue there. And we'll rerun generate data. And CP prog2 generate data, not generate data, plot data. Then plot data. These fields are going to be different, so it's going to be this is going to be task count and speed up. So X label will be task count, speed up. Okay, let's go ahead and plot data. Oh, we got to do our dot slash dot VM bin activate, and then we can run it. And then we can open up our data CSV PNG. Yeah, look at that. Got a 70x speed up. Okay, let's go back to right up, go back down here. Say I was able to get over a 70x speed up by using ABX 512 up to 32 tasks. And then I'll put in my little plot here, boom, which will be prog 3, like that. Go back over to here, kill that. View 1 has speed up of 8x over serial version, which is about 2x speed up of the regular ISPC without tasks. So able to get over 70x speed up by using AVX 512 up to 32 tasks. Any more than that, and I got inconsistent results, both in performance and correctness. The correctness issues cause concern, but seemed to not appear around 32 tasks up to. And then here I'm going to say cat proc CPU info grep. We'll grep for core ID, word count L 32 foreground. My machine has 16 SMT, 16 cores, each with 2 SMT threads. So it makes sense that performance would not improve beyond the use of 32 tasks. I was impressed that SMT allowed for performance, linear basically, linear performance gains past 16 cores, 16 tasks. For my 16 cores, I was under the impression that SMT workloads that were used SIMD, that workloads that use SIMD heavily competed with each other, say threads. I'm the impression that threads that use SIMD heavily compete with each other for SIMD resources when co-located on the same core via SMT, but that didn't appear to be the case here. Oops. Okay. Let's see, what else does he want me to talk about? Extra credit 2 points. What is the difference between thread abstraction used in program 1 and the ISPC task abstraction? Okay, let me do extra credit. There's some obvious differences in semantics between create join and launch sync mechanisms. but the implications of these differences are more subtle. Here's a thought experiment to guide you. What happens when you launch 10,000 ISPC tasks? What happens when you launch 10,000 threads? For this thought experiment, please discuss in the general case, i.e. don't tie your discussion to this given Mandelbrot program. Yeah, I'll take that on. The main thing is that use the thread pool. The smart thinking student's question, hey wait, why are there two different mechanisms for each and launch for expressing independent parallelizable work in the ISPC system? Couldn't the system just partition the many iterations of for each across all cores and also emit the appropriate SIMD code for the cores? Answer, great question. There are a lot of possible answers. Come to office hours. I won't be doing that. Program 4, iterative square root. Alright, so we're about halfway done with this. $8.16. I'll do the extra credit here and then I'll sign off for the day. But yeah, this wasn't a very difficult one. It only took me about an hour to get done here, so because it's just write up. It's like generate some graphs, write some stuff about it. This last one seems to be the most difficult one, the k-means. It's like you're doing a lot of programming stuff and plotting. Blast SaxPy. This one's seems to be fairly easy. 15, 10, 15. Okay. All right, let's get this one done. Well, let's jump over to ISPC here. There is no sink here. He's missing the sink here. Okay. Is it still dying? These are just integers, floats. Output's a pointer. None of these are... Yeah, everything gets copied. Maybe it's done in the main. Here. Is there a sink? No. Grip sink. Oh, doesn't hurt anything. I'll keep it in there. Okay. Jobs. Vim. Write up. Let's get this thing done. What happens when you launch 10,000 ISPC tasks? What happens when you launch 10,000 threads? For this thought experiment, please discuss in general case. I do tie your discussion to this given Mandelbrot program. Pretty much summarizes that. Okay. All right, done with that. Let's go back over here. Up here. All right, we are done with this. So get status. So what's going wrong here? Get DC. Okay, so we got our get ignore. We got our new data. We got PNG, that's great. We got a script to generate our data. We got our ISPC program that we made a change to parameterize the task count via a compiler macro pound define. We added the sync. We have a plot data thing, and then we made changes to write up. Oh, that's interesting. I don't want to include all that stuff. So jobs, vim, oops, write up. Let's actually fix that because it's kind of sloppy here. We'll just do D0 and put $1 here maybe to indicate the prompt. That's a little bit better. Get status, get add all. Get DC, go back down here. All right, that looks a lot better. We just scroll through here, that looks good. All right. Get status, get DC, what was it? Problem 3? Yeah, get CI, get LGA, get CI. We'll say complete problem 3, get push all, and then we'll CD back over to here, get status, get add all, get DC, get LGA, get CI. This will be a bump assignment 1. Get push all. Great. Cool. Let's go ahead and kill that. I'll leave this thing up. Open, jump over to assignment 1. Leave that open, and we'll do a little bit more research on that. These different libraries tomorrow. But it is 8:30. I told myself I would crash at 8:30, so I'm gonna get off here. Actually, tomorrow is Wednesday. I'm not going to be streaming tomorrow, likely, unless I just happen to find some time, because I got some stuff I gotta take care of Wednesday. But Thursday I'll be on. I'll be working on problems 4, 5, and 6 of this assignment, and probably watching some lectures, because I feel like we watched the first 2 lectures, and I feel like this assignment's getting to stuff that he hasn't lectured about. So, yep, cool. All right, I will be on Thursday around 1 p.m. at the latest. Cool.